Now let's take a look at our mass numbers on the periodic table. This is an interesting phenomenon. So the mass numbers on the periodic table, if you'll notice, are not whole numbers. You might have seen that by the last example we did with magnesium, where it's 24.31. Here's a really good example, chlorine. Oof, chlorine's at 35.45. That's how much this one weighs. AMU is the unit here. We're going to talk about units next chapter, so don't get too confused by that. Okay. So these are not whole numbers, which is weird because we thought, right, that protons plus neutrons equals our mass. Can't have half a neutron, half a proton, right? This occurs because of what we call isotopes. So isotopes are elements that have different masses. Same element, different mass. So it's chlorine, but it's got a different mass number. So for example, carbon's a great example. We've got 3 different types of carbon. We've got carbon 12, which is this one here on the periodic table because it weighs 12. This indicates the mass. We've got carbon 13 and carbon 14. They weigh different amounts, but yet they're all still carbon. What's interesting about this is that means that this number here, our atomic number, is the same. Because remember, if we change that atomic number, we change the identity of the atom. Now it becomes boron or nitrogen. It's no longer carbon. So what that means is that in order for it to be carbon, your atomic number has to be 6, which means these all have 6 protons. All 3 of them have 6 protons, yet their mass is different. So that means that another subatomic particle changes. So what subatomic particles can change mass? I think you can probably figure that out without changing the identity of the atom, and that is the neutron. Neutrons have mass, no charge. Okay. As you saw in the previous example where we looked at the magnesium, in order to find the number of electrons, protons, and neutrons in an atom, we have to round to the nearest whole number because of this problem, because of these isotopes that exist. In nature, we don't just have carbon 12. We've got carbon 13 and carbon 14 out there in the universe. And so that gives us our average mass. That's what's on the periodic table, is an average mass, atomic mass. So what you're going to find for like chlorine, 35.45, we're going to need to round to the nearest whole number. So in this case, if we round up, you'll see that this gives us to 36. Okay, so we're going to need to round up to 36. So that would be the mass that you use to find neutrons. So for chlorine in particular, it's got 17 protons. And if we wanted to find the neutrons, plus neutrons equals our mass equals 36. That's what you'd have to do there. So you'd take 36 minus 17 to find the number of neutrons. So do be careful whenever you're looking things. So boron, 10.8, you need to round up to 11 in order to find the neutron mass. Most of these are pretty close to what their whole number should be. Like you look here at 79.9 or 20.18, but there are some occasional ones like the examples I've just showed you where they are not too obvious and you will need to round. So let's look at kind of what isotopes look like in nature. So in nature, there tends to be one dominant isotope, which is why we tend to see that these masses are close to a whole number a lot of times. So carbon in particular, carbon on the periodic table is 12.01. So it's very, very close to 12. So in nature, we've got a lot of carbon 12. We do have carbon 13 and carbon 14, just very little of it. So if we looked at a log, there's carbon and wood, lots of carbon and wood. It's mostly made up of carbon 12 atoms. But every now and then, there's a carbon 13 and a carbon 14 isotope. And so what we see is in order to get these average atomic masses, what we're doing is we're looking at the isotope mass. This is the mass. Sorry. Mass. And we're looking at their percentages, and we're adding them all together in order to get the average atomic mass. So isotope 1, in this case, would be 12.0. And you're going to take the percentage of it. Here, it's very high. Let's say it's like 90%, 0.9%. I'm just estimating that number. I'm making that number up, okay? Isotope N means whatever isotope number that it is. It can, sometimes there's 2 isotopes of something, sometimes there's 3, sometimes there's like 6 isotopes of an element. It just depends on the chemical structure, okay? For carbon, there's usually only these 3. So for this one, carbon 13, 13.0. Oh, sorry. Let me go back. Okay, so for carbon 13, sorry, if we look, it's got a very small percentage. So let's say that it's like 0.08. So 8%. This was 90%. This was 8%. Remember that 90 over 100 is the percentage, and that's equal to 0.9. That's where I got that number from. And let's say that this is 13.0. That's the mass. This is our C13. This is our C12. And then our C14 gets added in there too. So let's say that that one's like 2%. That's the last 2% there. Okay, so 0.02. And let's say here that its mass is 14.0. This is our C14. And when you add all of these up, they're going to give you that 12.01, that average atomic mass. Remember, I made these numbers up, so if you put them in your calculator, they may not add up. But the idea here is that the majority of carbon is carbon-12, and therefore it contributes most to this mass number, which is why it's really close to 12, because the majority of carbon is carbon-12. So in elements like chlorine, you might see that these numbers, these ratios of the isotopes to each other are more dramatically shifted to some of the isotopes in particular. So let's look at an example with actual numbers. Okay, so these are real numbers. Isotopes, where we have different amounts of neutrons, so different numbers of neutrons, that's what an isotope is. They usually occur in very small amounts in nature naturally. The abundance is the percentage, and this is indicated by this fraction here, this percentage. Okay, whenever you see isotopes, we can write them 2 different ways. One you saw me do with the carbon, where you just have the element symbol and dash in its mass, or you can have it like this, where you put the mass to the top left as well. So we see our hydrogen isotopes here with a mass of 1, a mass of 2, carbon-12, carbon-13 masses. Okay. So let's take a look here at an example of, well, this is a bad example. Hold on one second. Yeah, let's take a look at silver, sorry. And this fractional abundance comes directly here from this. So ignore what I've got here. Okay, fractional abundance of isotope 1. So let's say the fractional abundance of this number was over here. Silver is not on here. Silver on the periodic table is the symbol Ag. So you would see this as Ag. It has an isotope of 107, and it has an isotope of 109, right? Silver. These masses are indicated here, 106.9 and 108.9 indicate the masses. In the abundance of these different ones, let's say they're 99.3 to 1, And then the rest here is going to be 0.789. That's the abundance of these. So you can see that 1 is very much dominant, which is our silver 107. So if I were to calculate these masses, I take this abundance, convert it into a fraction. So 99.321 divided by 100 is going to give me 0.99321. So that's the number that I put in here for our fraction, 0.99321. And then this next number here, we're going to convert that into a fraction. 0.789 over 100 is going to give us 0.00789. And so we put that number into here, 0.00789. And when you add these up and multiply everything out, so this is an addition symbol here, you find your average atomic mass. Okay, give this a shot with some real numbers. I promise these were actually pulled from a table, so they should equal out to everything correctly. So use your isotope abundances and your atomic masses of each of your isotopes in order to calculate the average atomic mass. Calculate the elemental average atomic mass of magnesium. So magnesium on the periodic table has what mass? So go ahead and pause the video and give this your best shot. All right, so in order to solve this problem, what we're going to look at is the abundance and the atomic masses. So we're going to write all these down. Now, when you do this, be very careful to use the full numbers. These are very accurate numbers. You might be asked as well to report your number to so many decimal places. So you're going to need to make sure you use these. If you round, you might get the wrong answer. Okay, we'll add these all together. 24.98584 times your percentage plus 25.9829 times your percentage. Okay. So when you put all of this math into your calculator, the number that you end up with is 24.3095 AMUs, or U. You might see it addressed as that as well. It's the same unit. Okay, so that's the mass if you look at the periodic table for magnesium. And that's because we have 3 different isotopes that comprise the magnesium that you're seeing on the periodic table. So that's it for topic 1.